Hello everyone, welcome to my talk. So today I'm going to talk about KENKU. My name is Shiqing from UMass Amherst. I'm an assistant professor there. So what is KENKU? So I think we all know a lot about adversarial machine learning and adversarial examples. KENKU is just one adversarial example generation framework against automatic speech recognition systems. So to give you some background, automatic ASR systems or automatic speech recognition systems, basically you give it a recorded audio, but because when we try to profile the audio, we usually have a lot of noises. So typically we'll have an algorithm to process the data, and then we use the translation model to translate the signal to a text. And the state-of-the-art models typically use a deep neural network to do the translation. And that's a basic background. And why are you guys here listening to this talk? It's because I want to give you something different, right? Something different from traditional works. My slogan is here. If you want to attack, you want to attack an audio system, but you don't really know who to attack yet. You don't know how to attack yet. You don't have a target even yet. How do you do that? We have you covered. Okay, so this is the whole idea of this project. So in other words, we want to support different types of attacks, including hidden voice and also integrated command attacks. We want to support the digital attacks and also physical attacks. And the threat model is kind of strong because we do not assume access to the model. We don't even want to query the model. So this means we have to be super transferable. So when the example is generated, it can be applied to a lot of systems. And another point I want to mention is it has to be very efficient, right? So these are the key points, or the selling points. Of course, we have some challenges because this is a pretty hard task. It's not impossible because I will explain this later. It's not impossible, but you need to do a lot of trade-off. And lastly, I want to mention that this is only part of the threat model. If you want to hear more about it, we have all the things in the paper. So in the next few slides, I will try to convince you this is totally possible and it's doable by presenting the details of this work. So this is a big overview of the KENKU system. So it's a very typical one. It has 3 stages. The first one is initialization. The second one is do the perturbation and optimization. And the last one is testing. So the key point here is I do not need to take feedback from the testing phase to optimize. So let's first rule out that part and focus on the real meat. So for the attack initialization, it's also pretty standard, right? So first of all, we want to have a target command or target audio. We can have public services and we translate to audio. And for hidden voice attack, in this attack, people try to add random noise to the target audio command and try to fool the system, which means the target audio will be the target command, the benign one, plus some noises, and the noise will cover the real command. And the other attack is the integrated command attack. Basically means if you are playing a song in the room or you are doing some normal activities, there are some noise. And the noise actually carry a command, and you want to fool the system. So these are all pretty standard. The hard part, as I mentioned earlier, is the whole optimization part, because we do not have any feedback from the target model. We don't really have a lot of knowledge. So simply put, adversarial example is a trade-off between 2 things. The first one is attack effectiveness, and the other one is imperceptibility, which means if you have the capability to totally change the audio, you can always make attacks, right? But the problem with this type of approach is the audio will be perceptible to human. We can easily detect that, right? So all the adversarial examples, you are trying to make a compromise between the two. You try to have a trade-off. In between, we have these adversarial examples, but how do we balance these two? That's a key problem in adversarial example generation. Our approach is actually very simple. So it's we have one loss function, and the loss function consists of two parts. The first one represents the attack effectiveness, and the other part represents the inceptibility. And also we introduce another hyperparameter here, which is lambda, which is a balance. We try to adjust this number to balance the attack effectiveness and also the imperceptibility. How do I determine the lambda value here? I will talk about later. And for LP, it's a typical perturbation. Okay, we want to add the perturbation to the audio, whether it's we want to maximize it in the hidden voice attack or we want to minimize it in the integrated command attack. That's very traditional. And the most difficult part actually is we want to make the attack succeed, right? Because in this case, we don't really know the target model. How can we say, okay, I added this perturbation, and after adding this perturbation, the command will get what I want? So this is the most challenging part. How do we deal with this? We actually take a very, very empirical approach, which is also the limitation of this approach. So remember, earlier I mentioned that in a typical ASR system, you have the recorded audio and you need to remove the background to do some pre-processing and then feed into the deep neural network to do the translation. So we take an empirical approach to study a lot of open sourced ASR systems, and we found that half of these systems are using MFCC as the data processing algorithm, which is not really surprising. But what's more surprising is a lot of other algorithms, not only MFCC are used, but these algorithms, mathematically, we can prove that they are extracting similar features with MFCC. What does it mean? It means basically you can have a universal approximation by using MFCC, and other algorithms like FBank and Spectrum, all the other algorithms, they are extracting similar features. And you may say, okay, it's not enough, right? Because one algorithm like MFCC is complicated. There are so many different parameters, and when you use these parameters, they have different results. And we did a deeper study. We found that MFCC, there are 5 different configurable parameters, and the values of these sets is very limited. I don't quite recall the number, but I think it's below 25 numbers, something like that. So which gives us a chance, right? So if we are doing this attack, we are basically trying to bypass one algorithm, which is a dominant algorithm, which is MFCC. And in this algorithm, even though there are many, many configurable parameters, their combination sets, the values, is actually limited. So if you bypass all these combinations, you are bypassing most of the algorithms, at least in the open source community. If the closed source community do have some more better algorithms or other fancy ways to do the data processing, it's likely our method will fail. But long history has told us MFCC is the algorithm we want to use because it's robust and its results are pretty good. So the solution becomes pretty simple. We just want to optimize by using MFCC as the criterion. And when we use MFCC and we try to feed into the DNN model, if the results, if the inputs of the DNN are similar, the outputs will be expected to be similar. So this is the basic idea. And now we have 2 loss functions. The rest part will be just trying to have a way to figure out the lambda value here. And we did an empirical study and on 5 different cloud systems, and here are the results. You can see that the ASR and the imperceptibility, which we use the ASR here, it's a signal noise rate. And you can see 2 different attacks, they are all basically linear correlated. Meaning that we don't need to have a fancy way to select the value, but a binary search perhaps will just do the job. Some people may ask, one is positively correlated, the other is actually negatively correlated, right? This is because these two different attacks, they are optimizing from different initialization. One is I have the target command, I want to optimize by adding noise, a lot of noise. The other is I have benign inputs, I want to add a noise as a carrier. So that's why they are, one is a positive value, one will be negative. And now let's talk about the evaluation to see if our design can actually do the job. And we have a few baseline works from existing published work, and all the target command and the carriers, all the settings are reusing existing work. We target 5 cloud services and 3 voice assistants. There are more results like larger evaluation results, but here I'm presenting the ones we can compare because a lot of state-of-the-art work actually takes a lot of time to optimize. So that's why they typically take 10 samples to do the comparison. And here is the digital attack, hidden voice, and the integrated command. The upper one is the hidden voice. The downside one is the integrated command. As you can see, most attacks can actually do a pretty good job by bypassing all the systems. And this is a physical attack for the hidden voice, and the y-axis is ASR. The x-axis include different distances from the source to the receiver device. And we have 3 different voice assistants. As you can see, our system is also pretty good, at least comparable with the state-of-the-art results. And this is for the integrated command. And we achieved, I think, for most cases, we achieved the best results. And here I have another one, which is the interpretability part. For the SNR result, SNR is using the objective function to calculate if it's imperceptibility or not. This is a user study. We actually asked many people to recognize, not only once, but sometimes twice, by playing the audio multiple times and ask if they can recognize or not. We also have the best result, and also we can bypass the existing defenses. We listed, I think, 4 defenses here. And lastly, I have some demos to show. So this is one of the traditional attack.
Open the door.
Can you guys hear it actually? Yeah. Okay, cool. This is another.
Open the door.
And this is ours.
Open the door.
So I call this the 1960s attack because it's kind of like the old cell phone. When you speak, it's also adding a lot of noises by the device. And lastly, I have some other demos. If you are interested, please come approach and I can show you. We also have physical attack demos as well. And lastly, I would like to conclude the talk. We proposed one system and it works pretty fine, that's all. Limitation is also pretty obvious because it's very empirical. We basically try to uncover the black box by studying what's inside the system. Thank you very much.